Hi guys, this is Unit 2, Nature's Chemistry. We are going to be doing topic 1, which is hydrocarbons. Most of this is revision from Nat 5, but we are going to put in some higher content as well. So we're going to recap Nat 5 knowledge of the 3 families of hydrocarbons and introduce some more complex molecules for systematic naming. Our success criteria is we can state the general formula for the families learned at National 5, name any molecule from its structural formula and vice versa, and we also want to be able to write addition-reaction equations. So, types of formulae then. From National 5, we need to know that molecular formula is written like so, with the number of carbons and hydrogens bundled together. Remember, your numbers have to be smaller and subscript. Structural formula is the structure side by side. So for ethane here, we have CH3CH3. Remember how you do this is to write the full structural formula and take a small chunk at a time and write those chunks one after the other. A full structural formula looks like this. You will be pleased to know that you don't ever have to write anything that complicated at higher. That's just an example of a structural formula of penicillin, but it's showing all bonds and branches, and that's what you have to draw for full structural formula. So alkanes then have general formula CnH2n plus 1. They are saturated molecules varying in size from 1 carbon, which is methane, to hundreds of carbons. The general formula, like I said, CnH2n plus 1. If you know the general formula, that can help you work out the number of hydrogens you need to the carbons and vice versa. You have this table on page 2 of your notes using your Nat 5 notes or knowledge, or if you're really struggling, you can look it up online or use BBC Bite Size. I want you to fill in the molecular formula, full structural formula, and shortened structural formula for each of those, please. It might be quite tricky to fit it into the boxes, but just do your best. So a little bit about boiling points then. Take a look at the boiling points of the alkane molecules as they get bigger. Why is this the trend? Well, as we look from methane all the way up to octane, we can see that the boiling points are increasing every time the molecules get bigger. Every time we add on a carbon and some hydrogens, we are jumping up the boiling point. What kinds of intermolecular forces are going to arise between alkane molecules? Are they polar or non-polar? Hopefully you are sitting there thinking, right, we've got carbons and hydrogens. They do not have an electronegativity difference big enough to be polar. They are non-polar bonds. That means the molecules overall are non-polar. So they're not going to have any permanent dipole interactions, no hydrogen bonding. They are only going to have London dispersion forces between the molecules. We know that these forces are weak, but we also know that as molecules get bigger, they contain more electrons, and the more electrons a molecule has, the stronger the force of attraction, the stronger the London dispersion forces between the molecules. So it's very, very important that we are able to make that connection with non-polar molecules like hydrocarbons. So butane, for example, has a higher boiling point than propane because it's a larger molecule. It has one extra carbon and obviously extra hydrogens, and therefore it contains more electrons. Remember how your London dispersion forces arise? They arise from a kind of electron shift. All of the electrons are found on one side of the atom at a time. So the more electrons you have, the stronger the force is going to be. Next family is the cycloalkanes. They are CnH2n. They are saturated molecules again, just like alkanes, but they are cyclic in shape, so they're kind of circular. Their general formula, as I said, CnH2n. Just like before, using Nat 5 knowledge, BBC Bite Size, whatever you like. These are on page 3 of the notes. I would like you to fill in the molecular formula, full structural formula, and shortened structural formula for each of these as well. You will notice that the boiling point trend is always the same. As the molecules get bigger, the boiling point increases, and that's due to the larger or stronger London dispersion forces. The next kind of thing that we haven't really discussed before is volatility. This is a measure of how easily things can evaporate. Since small molecules, so smaller hydrocarbons, are loosely held by weak London dispersion forces, they are more volatile. Now, this just means they're going to go from the liquid state to the gas phase very easily. For example, if you have been at the petrol station and you see when somebody's pouring petrol into their car, you have the fumes coming off the top, that just represents all of those little molecules going from the liquid phase to the gas phase because they evaporate so easily from the liquid. That's also how they get in our noses, because they're volatile and they evaporate. Lastly then, the alkenes are CnH2n as well. These are unsaturated molecules this time, and they contain the carbon-to-carbon double bond. Their general formula is CnH2n, which is the same obviously as the cycloalkanes, as cycloalkanes and alkenes are isomers of each other. Again, we have a table for alkenes. This is on page 4 of your notes. I would like you to fill that in just using the same methods as before. Again, the boiling point trend is still there because it's still true for all of the hydrocarbon families. Solubility, we have had a wee look at this before, so this should be very familiar. We did this as part of the bonding and properties topic. This is a measure of how easily molecules dissolve in liquids. So hydrocarbons, being non-polar molecules, mean they do not dissolve in water. We know that water is polar. It has polar bonds and is overall unsymmetrical, so it's polar. Hydrocarbons, all of them are non-polar. They don't have any charges, so they're not going to dissolve in water, but they do, however, dissolve in other non-polar solvents. For example, some dyes in clothes, I think this is your note in your notes, you might want to fill this bit in. Some dyes in clothes are made up of non-polar solids, so they would be dissolved in a non-polar solvent like hexane, for example, which then evaporates off of your paper or fabric or whatever you have, and that leaves behind the dye embedded in the material. So very, very useful for dissolving non-polar things. Isomers then, we kind of touched on this slightly. So remember, your definition for isomers are molecules which have the same molecular formula but a different structural formula. So examples here, cyclopropane, C3H6, and propene is also C3H6. As you can see though, they are completely different structures, which makes them isomers of each other. But remember, all of the cyclopropane or the cycloalkane, and alkene families are isomers of each other. So cyclobutane is the isomer for butene and so on. Here are some questions we'd like you to answer. Draw and name the alkane with 5 carbons. Draw and name the cycloalkane with 6 carbons. Draw and name the alkene with 2 carbons. Draw an isomer of butane. Which is more volatile, butane or heptane, and why? Explain why octene has a higher boiling point than propene. Explain why non-polar molecules dissolve better than hexane in water. Now take a look at the marks here. You have a 2 marker or two 2 markers and a 3 mark question. So we're going to be looking for 2 bullet points for the 2 markers and 3 for the 3 mark question. So I'd like to pause the video, try those questions in jotters or paper, whatever, and then play once you're ready to hear the solutions. Here are the answers. So number 1, alkane with 5 carbons is pentane. So make sure that you have your bonds going directly from your carbon to your hydrogen. And make sure you draw them nice and neatly so that your marker can see all of your bonds present. Remember, make sure that every single carbon atom has 4 bonds attached to it. This is a valency of 4. Next one was the cycloalkane with 6 carbons, so that's going to be cyclohexane. Again, make sure that your bonds are not floating. Make sure they are directed at the atom that you want, and that is drawn very neatly and clear. 3, the alkene with 2 carbons is going to be ethene. An isomer of butane would be 2-methylpropane. What I like to do with isomers is just take the molecule, take a carbon with its hydrogens off the end and stick it in the middle, and that gives you an isomer. So it's 2-methyl propane, in other words, propane with a methyl branch on carbon number 2, which is the middle. So 5 then, I'm just going to move this. So butane is more volatile than heptane because it is a smaller molecule. So number 1 for recognising it's a smaller molecule. Number 2 mark comes from saying that butane has less electrons than heptane, and so it has weaker London dispersion forces between its molecules, meaning that the molecules can evaporate more easily. So 1 mark for each of them. 6, this was a 3-marker one. Octene has a higher boiling point than propene because it is a larger molecule. It has more electrons then, and so the London dispersion forces between molecules are much stronger forces of attraction than in propene. The last mark is awarded for more energy is required to break these, giving rise to a higher boiling point. Remember, most people stop after mark 2 and they don't actually say how it relates to boiling point, so you must say that more energy is required to overcome those forces, which means it's going to have a higher boiling point. Last one then, I think. Non-polar molecules dissolve better in hexane because it is also a non-polar molecule, and like dissolves like. Water is polar, therefore non-polar substances will not dissolve in water. Something to that effect for both marks. Okay, so that's kind of the first little chunk of lessons. If you want to pause there and watch the rest of the video at another time, that's fine, but I'm just going to continue and do the whole thing in one video because it is kind of short. So, the next part is going to be a recap of systematic naming. So here's a little reminder of how it's done. First of all, step number 1, you are going to identify your longest carbon chain. Now be very, very careful, and I would honestly count it along with my finger to make sure that I'm not missing any carbons, because sometimes the structures are very complicated and it's not always the horizontal chain that's the longest, so watch out for that. In this example though, the longest chain is 4, so that's butane. It's saturated, so we can say it's got an ane at the end. 2, let's have a look at the branches. We have 2 branches. Both of them are methyl branches because they contain 1 carbon. And they are on branches 2 and 3. It doesn't matter which way you turn the molecule, they're still going to be the same numbers. We use a comma between numbers and a hyphen between numbers and letters. So this is going to be 2,3-dimethyl butane. So example 1 then. We have to name this molecule. So using the same logic as before, the longest chain I can see here is 1, 2, 3, 4 carbons, and it does happen to be the longest horizontal chain. It does have a branch which is on carbon number 2, and it's a methyl branch. So we're going to have 2-methyl butane, like this. Example 2. This one is a little more complicated, so listen really carefully. You do have a list of naming rules in your notebook as well, so make sure you're using them for practice. So let's number the carbons. So this is carbon number 1. Where these join, even though there's not a letter, this is called a skeletal structure. This is carbon number 2, where the mouse is right now. Carbon number 3 is therefore here. 4, 5, and 6 at the end here. So that's going to be hex, the prefix for 6. But we have double lines, which means we have double bonds. Now we have 2 double bonds, so it's going to be hexene, okay? But because there is 2 of them, then it's going to be diene. Okay, we need to tell where the double bonds are going to be as well. So they are on carbon 1 and 3. So we're going to have hexa 1,3-diene at the end of our molecule. Let's check that we have, we do have a branch. We have a methyl branch and it's on carbon number 1, 2, 3, 4. So we are going to have 4-methyl hexa 1,3-diene. You might want to watch that wee bit a couple of times. Make sure you understand where the numbers are coming from. close that wee bit there. So that's 4-methyl hexa 1,3-diene. Remember, pay attention to your commas and hyphens as well. Last one then, we have cyclopentane as our kind of longest chain, and it has 2 branches on it, and the branches are in carbon number 1 and 2, 3. So that's going to be 1,3-dimethyl cyclopentane. It will take you a wee bit of time just to number your carbons and make sure you're naming everything properly, but by the time you practice it lots and lots, you'll be able to do it as quickly as I can as well. So, some more questions then, just before we finish up. Draw the chemical structures for the following compounds. So what I'm going to do is I'm going to allow you to pause the video again, draw your structures, and then check them against mine in a wee second. So I'll just show you each of my drawings and you can check them and make sure that they are correct. So the first one is 3,3,5 trimethyl hexane, which looks like this. B is 2,2-dimethyl hexane, which looks like that. This is ethyl cyclopropane. 1-ethyl 2-methyl cyclopentane. 2-methyl pent 1-ene. 2,3-dimethyl hex 1-ene. Okay, the last kind of chunk of this section is a recap on addition reactions. Now remember, addition reactions occur when species are added across the double bond. So here we have like an XY molecule, the double bond opens up like a little gate like that, and the atoms join onto where the double bond used to be, in other words, straight up from the double bond. Alkenes, remember, are unsaturated molecules and rapidly decolorise bromine solution. That is your test for unsaturation, and you are expected to still know that information at higher level. So remember, the bromine molecule, Br2, adds across the double bond and decolorises rapidly in the presence of alkenes, but not alkanes and not cycloalkanes, because both of them are saturated. So here are some examples I would like you to try. Example 1 is reaction of propene with bromine to form 1,2-dibromopropane. So again, our double bond like this is going to open up, your 2 bromine atoms are going to join on, and you end up with it looking like this. There's space in your booklet to copy these examples in. Example 2, reaction of ethene with fluorine to form 1,2-difluoroethane. Again, double bond opens up, fluorine atoms join on, and it ends up looking like that. 3, reaction of propene with HCl this time. Now note that there are 2 possible products here. Where we have a compound joining on that has 2 different elements in it, they can be the normal way, how they're written, but they can also be flipped. I'll show you what I mean. So if the double bond opens then, and the hydrogen is on the left and the Cl is on the right, then you end up with the chlorine in the middle of the propane molecule. So it'll be 2-chloropropane. You can also have where the chlorine is on the left, so where the hydrogen and the chlorine have flipped, and that is going to be it's on carbon number 1, so it'll just be chloropropane. 4, reaction of propane with water. Again, this is something where we have 2 possible products. Remember, water is made up of a hydrogen ion and an hydroxide ion. So again, depending on which order they join on across a double bond, you can have propanol, so propan 1-ol, or you can have propan 2-ol. So it depends where the OH group joins on. It can join on the first carbon, or it can join on to the second carbon. Obviously, remember, if it joins onto the third carbon, that is still the first carbon if you turn that molecule around. So it's propan 1-ol or propan 2-ol which are produced. So we wanted to be able to state the general formula for the families learned at Nat 5. Name any molecule from its structural formula and vice versa, and draw the structural formula from the name, and write equations for addition reactions. Hopefully you have found this video useful in doing all of those things, and we will do a little recap and show me board exercise in class. Hope you have a great day. Bye.